Okay, so what we're talking about today is an introduction to the periodic table, and we're going to start by going over some of the history of the periodic table. Where did it come from? Who put it together? What parts does it have? A little bit of background information about the chart that we pretty much use all the time in chemistry. Now you've gotten used to using it a little bit. You're used to having it on your tests and on your homework. So over the next 4 weeks, 4.5 weeks, this is when we really kind of go in depth with how it's organized and what other information we can get from it. So starting with some history. There are some elements off the periodic table that have been known for a very long time. Some elements were known and used by ancient civilizations, including like the Romans, further back than that, medieval times, further back than that. If you think about early human history, there are, I think, three time periods that have names like the Stone Age. Remember what the other two are? The Bronze Age and the Iron Age. Iron we know is an element just by its name. Bronze is actually made of a couple different elements, but you can use that knowledge to kind of think about this idea that there are some elements that have been known to humans for a very long time. Can you add any more elements to the list? We got the iron. What else do you think we've known about for a long time?
Oxygen.
Oxygen, maybe? We certainly have used it for a very long time. That one might be a little harder to discover because it's a gas. It's not something you can see. Think about things you can see. Think about money. What they use for money. Gold, silver. Those kinds of elements have been known and used for quite some time. Here are a few other ones. Carbon and sulfur. Carbon is what's left over after you burn something, like a chunk of firewood. What's left is mostly carbon. Sulfur is a mineral that's formed naturally in the ground, so that was one that they knew of. Sulfur is bright yellow, if you haven't seen it before. We'll get some of these elements out in a week or so, and you'll get to actually look at what they look like in their natural state. Copper, silver, and gold. These are the ones that were typically used for trading or for money. And a few other ones. Iron, of course, we mentioned. Tin, antimony, and lead are a few others. Fast forward a ways, during the time period from 1000 AD to 1869, so we're from kind of the Middle Ages through almost what we consider to be modern times, 63 new elements were discovered by alchemists. Does anybody know what an alchemist is or was? An alchemist was a person who was trying to combine science and magic. So kind of Harry Potter meets chemistry class. Alchemists were ultimately trying to take lead, which was very abundant and very common, and see if they could change it into gold. Because of course if they could change it into gold, then they'd be rich, and they'd never have to worry about money again. So they were combining whatever science they knew at the time with other things that they believed in, which we would probably classify as magic now, and change lead into gold. Along the way, though, they actually produced or discovered some useful things for us, and a few of the elements that they were responsible for discovering include arsenic, which we know is poisonous, zinc, which is very commonly used to keep things from rusting, phosphorus, platinum, nickel, nitrogen, oxygen, chlorine, and aluminum. So you take the elements that we already knew from ancient times, plus the elements that the alchemists discovered. I don't have an exact number, but we're probably somewhere between 63 and 90 elements or so. We're starting to collect a lot of information. That's a lot of elements to learn about. But up until this point, nobody had taken the time to try to organize the elements or to classify them into groups. And that's where this guy comes in. Dmitri Mendeleev. He was a Russian chemist. Students usually tell me his picture is kind of scary looking.
He looks like a hobo.
He looks like a hobo. That's a new one. Dmitri Mendeleev was responsible for creating the first periodic table in 1869. He was the first person to take all the elements that we knew of and try to put them into groups or organize them into categories. He did that by arranging the 63 elements that he knew by their atomic mass. He took those first 63 elements that he knew of and he put them in order of atomic mass. Atomic mass is something that they were able to calculate because if you take a certain amount of an element, put it on a scale, you can get a relative mass. Take the same amount of a different element and put it on the scale, and you can compare how much those two weigh. And then he also puts elements with similar properties in groups together. Elements that behave the same way when they react with things, elements that have similar physical properties, he puts those elements in groups. So he arranges them by atomic mass and puts similar elements in groups together. By doing this, he comes up with a chart, and it's a very kind of similar looking chart to our current periodic table, although there are some key differences. And he notices that there are holes in the chart that he's created. And so from those spaces, he's able to predict the existence and properties of new elements that hadn't been discovered at that time. I don't expect you to write this down, but this is a picture of what Mendeleev's first periodic table looked like. So you can see he started with the lightest element, which was hydrogen, and then he's got the rest of the elements in order of atomic mass. Lithium at 7, beryllium at 9.4, boron at 11, carbon at 12, and so on. So the atomic masses go from left to right. Then he's taken elements with similar properties and put them in groups, and the groups go up and down. So things like lithium, sodium, and potassium are very much similar in the way they look and the way they behave. What he ends up with then are holes in his table, like here. He should have an element whose mass is about 44. That would be halfway between calcium at 40 and titanium at 48. But at this time, that element hadn't been discovered yet. So based on where it is, underneath boron and aluminum, between calcium and titanium, he can predict that this element should exist. And to a certain extent, he can predict what it will be like. Is it a metal? Is it a solid? Does it react with water? Does it react with something else? He can predict some simple properties and also, to a certain extent, the mass of that element that he's missing. And this was pretty revolutionary at this time because nobody had done this before. Nobody had taken all these elements and organized them into a chart before. After that, we fast forward about 30 years, a little bit less, and we have a Scottish chemist named Sir William Ramsay. And Sir William is responsible for the discovery of neon, argon, krypton, and xenon. Do you know what those elements are called or what their category is? The noble gases. The noble gases. And so he adds a new column to Mendeleev's table, and he calls it the noble gases. They're called noble gases because they really don't react with anything. Eventually, when we get to the test, you will have to know who is responsible for what. I'm not going to ask you specific dates, but I will ask you for people. Who is responsible for discovering what? And the way that I always remember that William Ramsay is with the noble gases is because his name is Sir William Ramsay. Yeah, he's got a Sir in front of his name. So if you know anything about medieval history, you know that that title usually goes along with somebody who is considered to be a noble. So Sir William Ramsay discovered the noble gases. Fast forward a little bit, about 15 years this time. Henry Moseley was a British physicist, and I believe he died in the First World War, which would have been right after this discovery. He's responsible for determining the nuclear charge. And if you think about that for a second, you'll realize that that's really just the number of protons. Because what two things are in the nucleus? Protons and neutrons. Do neutrons have a charge? No. So the nuclear charge is just the number of protons. So he's responsible for determining the number of protons in each of the elements that we knew of. And he takes Mendeleev's table and he rearranges the elements by atomic number. And this is the system that we currently use. All of our elements are arranged by atomic number. It does, for the most part, follow along with atomic mass. As you add protons to the nucleus, your element gets heavier. So it would make sense that those two things, the mass and the atomic number, would trend together. In other words, they would both go up at the same time. There are a couple of spots where this does not hold true. If you look at, let's see if we can read it, cobalt, nickel, and copper. If you're going by atomic mass, cobalt and nickel should be switched. If you go by atomic number, then you have the current arrangement that we have over there. So most of the time, atomic number and atomic mass trend together. If one is higher, then the other one is higher. There are a couple of spots, and cobalt and nickel is one of them, where those two things would be switched around. So Henry Moseley discovers the nuclear charge, and he rearranges the table by atomic number. And then we have one more discovery for our modern periodic table, and that was the contribution of this gentleman here. His name is Glenn Seaborg. He's actually an American. This was circa 1946, so fast forward a little bit again. Seaborg is responsible for rearranging the table to add the actinides. Do you know what the actinides are? The actinides and the lanthanides?
The ones in the bottom?
Yeah, those are the ones on the bottom. Those two rows across the bottom of your periodic table. And I don't have those on the one on the wall simply because I don't have enough space to have them up there. We don't use them all that much anyway in this class, but he was the one who took all of those newer elements and put them down underneath into the actinides and the lanthanides, those two rows there.